From TÜV SÜD, a certification organization doing all kinds of certification, mostly when it's about safety, product safety, general, but all kinds of other certificates. As soon you find a regulation, a standard, or whatever, then you can be sure that TÜV SÜD has some certification scheme around that. But really, I think the core business is safety, product safety, traditionally. TÜV sometimes, it's a bit confusing. What TÜV? Is there one TÜV and are there regional TÜVs? Well, right now we have 4 different TÜVs left, I should say. 20, 30 years ago, we had really as many regions as there were or still are in Germany, and in the 90s it got privatized, and since then all these TÜVs have continuously consolidated, and now we are 4 left. We have TÜV SÜD, TÜV Nord, and TÜV Rheinland, and we have under SGS also a smaller one, still TÜV SÜD SA. We're competitors, commercial competitors, but still do not completely forget our roots and our, let's say, original mandate. So we still coordinate on an informal basis, but want to make sure that we somehow have the same interpretation of standards, same approach about it. Yes, around since 150 years, and present globally, I think currently 228,000 employees. When it comes to functional safety certification in particular, then we distinguish between these service, of course, the core business, product certification. Whenever a product requires compliance with the standard, regulatory compliance with the standard, or be it just a driver from the market, then that's what we primarily do. Safety-related control systems, subsystems, components, elements, whatever the standards use. Typically generic components, that's what we mostly do. The C, according to 26262, I've heard that safety element out of context, or compliant item, that's what the standard IEC 61508 uses as a corresponding term. Tools is a relatively new business. The automotive standard was a main driver to also have development support tools, qualified, pre-qualified, and there is a request from the markets to have also a stamp from someone like TÜV SÜD or our competitors for such pre-qualified tools. And you can use 26262 also as a kind of quality management standard, and we do organize processes, organizations, product independent. So essentially trying to find out whether an organization has the maturity level, is prepared to start development of complex safety-related control systems. Training is another relatively big topic, because functional safety and the standards is still seen as something complex, something that you maybe did not hear too much about at university or engineering school. Cyber, we also cover that, but it will not be the topic of my talk today. Focusing on functional safety. If you do trainings with us, you can also pass an exam, and then you get a certificate that you now are a certified functional safety engineer or expert or professional or guru or whatever the title may be. And then we have a bit more informal services. We could call it advisory or more informal feedback, analysis, testing. So we do that kind of consulting or advisory to the extent that, of course, our status as an accredited certification organization allows us. We must not violate these requirements of independence and impartiality. So what we do is the same thing, the same activities that we also do for formal certification, just in a more informal way. That's what we can do in as advisory services. All right, the agenda for today, or the topic is certification, functional safety certification. So what is suggested is that we have a very quick introduction to the basics of functional safety. I'm pretty sure that many of you have quite a good understanding what this is, just to set the framework for the rest of the discussions. Yeah, what is it? What are the major challenges? And then in particular, we want to focus on assessment. What is that? And what is certification in that context in particular? Ideally, something very similar. And we'll then also speak about what could be motivations for certification, why you want to do that. Also a little bit what TÜV SÜD wants to achieve here, what TÜV SÜD sees as an added value. So a bit of commercial talk, I think must be allowed. But yeah, we think it's a good service, so I will speak about this. And then in the end, a bit of the experience we have with the many projects we have with customers from all industries, from all over the world at all levels, complete applications down to low-level elements like software libraries and hard soft IPs and so on. Right. Functional safety clearly exists if safety depends on the correctness, appropriateness, reliability, integrity of control functions, of complex functions inside systems. Such functions at a high level can be protective functions, so these would be functions that you add to a system to achieve safety. So this could be typically some things you have in machinery, like light curtains, tread mats, safety doors, and things like this. You don't need these devices and their related function to actually have a productive machine. This is just for safety, just for protection of the workers, of the operators. The other type of functions which can be critical, of course, control functions which are essential part of the product, of the device, of the machine that we're looking at. And a good example for this is, of course, automotive. You have especially automotive with in mind additional or going into autonomous driving where basic driving functions then have to be implemented using complex electronics and software. So these are functions that must be there in the vehicle, but if they have a malfunction, then of course it will not be very safe. So you have safety requirements on these functions too. Another good example would be avionics, flap control and so on. These must be made compliant with safety-related standards as well. Functional safety really applies across the board, all domains, all product types. We do have safety-related control functions, be these basic control functions or be these additional protective functions. The main issue or the reason I would think really we do have functional safety standards or we do have functional safety as an engineering discipline is the fact that we try to replace conventional technology, mechanical links between an input device and an output device by electronic means, by computers and software. So steer-by-wire, for example, instead of a mechanical link between the steering wheel and the wheels on the street, we got rid of the steering column and replace it with sensors, computers, and then maybe an electrical drive that moves the vehicle. So you ultimately could drive the vehicle, the truck, even with a joystick, right? And you wouldn't need to have a really mechanical device to gives some torque, and that torque is then maybe fortified and amplified and transmitted to the steering wheels. And that by itself, one system, of course, is complex. Everyone of you who is electronics engineer, software engineer, then that is very complex. Complex in the sense that the software that will run on the processes that you need cannot be 100% fully tested. You cannot come across each and every state or each and every path at runtime. So you cannot run a full formal safety-proof product specific, right? Yeah. And that complexity, well, you see here, maybe what today or until maybe a few days ago, a modern car looks like. We have dozens and dozens of electronic control units, each of them by themselves, very complex, of course, but we also have a functional complexity on top of that, often functions which maybe are antagonistic when it comes to safety, functions which whose safety relevance may be driving scenario, driving situation dependent. So we get an extreme complexity here. And functional safety is really the answer to get to some level of confidence despite of the complexity. That's why we have functional safety. And the answer in short is, if we cannot run a full proof on the product itself, then we just look at the processes they use. If they do proper work, if they use a lot of time and effort and depth and hopefully formality in designing, specifying, testing, and so on. So that's essentially what functional safety is about. And I think that complexity doesn't stop here. It keeps on growing exponentially. I think you had a good presentation by Hult with such an exponential curve for the Internet of Things. Same is true, of course, for the automotive. If we look into the very near future, we have more and more automation, automated driving being currently the holy grail of automotive. Require more complex sensing, more intelligence, artificial intelligence. And we have a system of systems. A vehicle is no longer a separate machine, but it's interacting with other vehicles, interacting with the infrastructure to the extent that really more and more it gets clear that the automotive industry no longer can get away with being responsible for the vehicle and making them safe, but it turns more and more into an issue of public safety, in fact. And this can also be seen in the regulations in relation to functional safety. We'll see that a little bit later. What are the functional safety challenges? Again, the basic challenge is complexity. And first, that complexity will be a challenge just to identify what is safety, what are the safety functions, what are the malfunctions of safety functions, maybe interactions with couplings between different functions. The very first step, in fact, hazard analysis and risk assessment that we need to do is already more and more becoming an immense challenge in terms of complexity. In machinery, maybe it's a little bit easier, most importantly because in machinery, kind of if you pull the plug, if you shut everything down, everything stops, nothing moves, then in 99.9% of all cases, you're safe. Okay? So that makes it a little bit easy. However, complexity also increasing here on an application level. Robotics, we have collaborative robots, complex interaction with the workers, with the operator. We have Industry 4.0 or the industrial Internet of Things also here. A lot of complexity is actually added. But well, how to conduct hazard analysis and risk assessment, I think in the automation machinery context, it's essentially the standard ISO 12100, which has this approach here that, of course, a robot like this is way too risky. It's a really dangerous machine, in fact. You have to reduce the risk to what is acceptable. What you could do, of course, put the whole thing in a cage, then not really much can happen anymore. No one can ever get close. No workpiece can be flung off and hit someone. Either, but not a very usable system. You want to have a door in that cage because you need to come close to teach, to maintain, to clean, or whatever, from time to time. So if you have just this door here, then of course it may happen that you forget to close the door and start the robot up again, or someone is inside and someone else doesn't see it, wants the robot to work again and switches it on again. Okay, so that the risk reduction is no longer perfect here. To some extent, yes. To a good extent, we do get risk reduction from these conventional means, and standards do require to do as much as possible with, let's say, normal, common sense, conventional risk reduction. Inherent safety is another term for this. Only what you cannot really get rid of in terms of risk, that's where you would need safety guards, where you need protective systems. And these protective systems typically, especially the active ones, of course, implement complex electronics. There's some sensing, there's some processing, and so on. Also, that may be not perfect. In this particular case, of course, we would want to have sensors here at that door, a position switch, something which detects that the door is open, and then sends hopefully reliable signal to the robot controller to make it stop, or maybe to run it at a safely reduced speed. Okay. That's what you want. Otherwise, you cannot teach anymore. You want to have a robot that moves, but you want to have the safety guarantee that it can never exceed a certain speed, which could be dangerous for a human being. Of course, if you do that, then there still may be misuse, or then simply that you install this safety door logic wrongly. Misuse can also be that maybe workers get annoyed by it and try to bridge it and so on. That's in fact one of the main sources of accidents at the workplace, even though there are protective devices. The workers feel it's just annoying and they disable them. So all these things, so instructions, and yes, as the machine manufacturer, also to cover yourself maybe legally. There's also the instructions of use. Okay. All right, yes, and the more we rely on risk reduction by guards like this, by protective functions, the higher the integrity of these devices must be. And this integrity, or that risk reduction, is measured in these levels. Standards, different standards have different levels, integrity levels. Most famous one, of course, safety integrity level by 61508 and derived standards, product standards. And the other big player in machinery still dominating, I think, at the machine level is ISO 13849 with its performance levels. In automotive, 26262, we have another view here, another diagram. The acceptable risk here would be shown as this curve in the severity probability diagram here. If you're below that curve, then you have acceptable risk. If you're above that, it would be unacceptable. You have to do something about it. You have to reduce the risk by appropriate integrity. In automotive, you have a normative hazard analysis. It's part of the ISO 26262 standard. You always have to do it. First you determine severity, then determine probability of occurrence. The particularity in 26262 in automotive is that probability of occurrence is uniquely about exposure. You only are allowed to reason about how long, what percentage of time or how often does safety of driver and passengers and bystanders depend on the fact that a particular function has no malfunction. You are not allowed to consider, well, what is the probability of that malfunction? You may not consider it at the risk analysis step. Okay? You have to abstract from it. That was decided by the automotive industry because, of course, if there's one thing that all automotive manufacturers, all OEM want to have and want to boast about is reliability, availability of their vehicles, and it was felt that it would end in never-ending discussions that, well, everyone would say, our vehicles are so reliable, we don't need that ASIL stuff, okay? We don't need that functional safety thing. Things never go wrong. So to rule that out, it was really said, and it was the OEMs and the Tier 1s who wrote the first version of that edition of that standard, who decided that you are only allowed to reason about exposure. Okay? So that's important. For an airbag, for a very simple system, we have two, let's say, safety goals, safety functions. One is, of course, to do what it's supposed to do to protect if in case of a heavy collision. But there's another safety requirement, another safety goal. This is, of course, not to deploy, not to blow up unintentionally, spuriously. Okay. Now, the severity in both cases is bad, right? If you not get protected in a crash, then you will get bad injuries, can be lethal. If the airbag explodes while you're driving with 150 kilometers per hour on the German motorway, very bad too. Okay, you may be knocked unconscious. An accident may be the case. So no doubt about severity, but probability of occurrence exposure is quite different. So when does your safety actually depend on the fact that the airbag does what it's supposed to do to protect you in case you have a severe collision? Of course, only when you have a very severe collision. Okay? And that is something that, gut feelings, from my own experience, never happens. So I've never had a crash where I would have hoped that there was an airbag. Okay? And I would think the same is the case for most people. So gut feelings, once every 10 years or so, if you would have to put a number on this. Okay. How about the other safety goal, to not explode unintentionally? When does safety, how often does safety depend that this malfunction does not happen? All the time. Whenever you sit in front of the steering wheel, your safety depends on this thing not just going off spuriously. So you have extreme high exposure rate. Okay. And then there's also driver responsibility, controllability. The driver is expected to be compliant with the law, have a driver's license, respect traffic rules, not be under the influence of drugs and so on. And if everything goes wrong, in some cases, driver may still mitigate to maybe reduce the severity or maybe dodge the collision or so to reduce the exposure. Anyway, you will end up somewhere up here, and this is not acceptable. And that's now when we reason about integrity. That means that particular function must be implemented with an appropriate integrity to reduce the risk to an acceptable level. All right, once we have identified safety, functional safety, we have the functions, the malfunctions, we have identified what the risk level that is associated with it, then we need to achieve functional safety by simply achieving that integrity. And this is really where we can say the SIL or ASIL or performance level, they have a double role. Up till now, SIL, ASIL performance level was a metric of risk, was a metric simply of risk or required risk reduction. And now these turn, in fact, into technical requirements in order to make an implementation of that particular function with a commensurate integrity that provides this risk reduction down to an acceptable level. Okay. So that requires safety integrity must mostly be concerned about the fact that things go wrong. Okay. Hazard analysis in functional safety, the main hazard is malfunction of an intended functionality. So we reach integrity if we make sure that these malfunctions don't happen or don't happen too often. So we need to be failure focused. That's I think the fundamental mindset of safety engineer, functional safety engineer, not to think only in positive terms about the thing you want to do. Great new feature for your vehicle, great new function in your robot and so on. You have to always think about what if something goes wrong. So you have to have this critical attitude to your own work. And failures and faults, all standards classify them in two main categories. Now first, let's say the traditional, the classical ones, which are conventional, classical, old-fashioned safety engineering. We have, of course, hardware components, and everyone knows that these will fail. These have a failure rate, these have a useful life, there is failure rates for it, there is a B10 value or whatever. So, and clearly, some point in time, you have a failure, so we must have a design that is prepared for it, that can tolerate it, redundancy, that can detect it, any diagnostic safety mechanisms. And of course, we also want to have some good level of reliability of these components, and standards state requirements about such a concept and architecture based on redundancy diagnostics in a quantitative way. In fact, under a particular SIL or ASIL, you have metrics, parameters, metrics, which quantify, let's say, the goodness of an architecture to be able to control random hardware failures. Okay? That's random hardware failures and control. The other one are failures are systematic failures. What are systematic failures? They're called systematic because they always will occur and manifest themselves in precisely the same way. According to the standard, there is no randomness to it. It's more deterministic. If certain conditions are true, the fault will happen. Okay? The failure will happen. The main root cause of systematic failures is not, let's say, the laws of physics, as over here, but it's ultimately human mistake, human error. Mistakes, errors made by developers, implementers, testers, installers, and so on. Okay. And the key approach to systematic failures, to dealing with systematic failures, is not really control. It's actually avoidance. And who does avoid? Who makes the avoidance? Well, it's the hard work that we have to do as, again, designers and testers and installers and so on. Okay. And well, how do you avoid making defects? How to avoid making bugs in software in particular? Well, it's hard work. You have to follow good processes, good documentation, try to be formal to the extent possible and appropriate, and a lot of testing, verification, validation, so on. So these two faults, they of course are reflected by, let's also two types of requirements. We have, say, the process-specific requirements, functional safety management requirements, processes, methods, and tools requirements, and we have, let's say, the product-specific requirements that tell you how to construct a good safety architecture. Yeah, just quickly, some visuals here. We will not discuss this in details, but avoidance of systematic failures. We have processes, methods, tools. We have a high-level safety life cycle, functional safety management. It's based on this, and then we have detailed processes, especially on the software side. The V-model approach is a fundamental principle applied by all functional safety standards as a main approach to avoidance of failures, avoidance of design defects, right? Modular design, continuous refinement, and continuous verification, and then you develop. Same time you develop your system, you also have to develop the test specifications at all levels. Okay? That's what the V model tries to show, that you you design for test, you design for verification. That's one of the key aspects of the V model. And then within each of these phases, you have then very detailed requirements, what precisely kind of techniques and measures and methods you have to apply depending on what the safety integrity level is that you want to achieve. The higher the safety integrity level, the more rigor, the more highly recommended you will find in the corresponding columns. Okay. Regarding control, random hardware failures, it's about a good architecture. That's essential. Something that has redundancy, as in this example here, that has diagnostics. You see diagnostic feedback lines here. That's probably something that should give you a good SIL 3 category 4 system for SIL 3 category 4 safety PLC, or also for an ASIL-D, I think, even in a fail operational scenario, if each of these microcontrollers by itself has a good level of self-test. And you can, of course, fail operation would mean you cannot just be happy with detecting a discrepancy. You must locate the fault. You must know which of the two channels has faulted. Okay. All right. That's all, right? So identify safety and then achieve safety. Then we're safe. Are we done? Not quite, because things change, especially if they're software intensive. They will be modified. The positive view of this would be that you have a good interest by customers and they come along with new features that they want to have implemented. That's, of course, the positive thing. The negative thing is that you have field returns and bugs you need to fix. Doesn't matter, in every case you have change, and a big challenge is to maintain the safety integrity if you have change. And this, how do you do this? Well, this comes again back to the processes. You need to have good processes in place, especially good change management based on impact analysis, and such an impact analysis, in order to be able to make it properly and good one, to know what is actually affected, what are the impacts of a change. We need requirements traceability. That's a key measure that, let's say, in addition to the V model, which standards require for achieving systematic integrity. And requirements traceability really is required to be white box traceability from high-level requirements, kind of a vertical traceability into the design, into hardware design, the lowest level, into software design, down to unit level, function level, maybe even lines of code level. Document management, and then also configuration management, release management, to make sure that a particular then fully assessed, validated, maybe certified version is actually released into the factory floor or onto public roads. All right, then we're done, right? Or is there missing something? Well, this is very good. However, it's not only half the value, or maybe has no value at all, if we cannot demonstrate that we have achieved, and if we cannot demonstrate that we maintain. So we need to demonstrate, we need to prove it to ourselves as the manufacturer. We want to have, of course, a safe product. We don't want our customers or end users to get hurt. And sorry, we have to demonstrate. That's the real challenge because of the complexity. So we have to demonstrate to ourselves, we have to demonstrate to our customers. If things go very bad, we may have to demonstrate to a judge, to a lawyer. If an accident happens and everyone looks for who's the culprit, who has most of the money, I don't know, then we need to be able to demonstrate that we actually have achieved safety. And that's where, let's say, the ultimate level functional safety assessment comes in. That's the final, ultimate judgment that a product is safe, functionally safe. But if you try to find out in the standard, try to read them carefully, what actually is required, how do you do a functional safety assessment, what are the precise activities, it's a bit vague. It's a bit vague, in fact, especially in 61508, I think. 26262, I think, has an improvement here. It does something that hopefully the third edition of 61508 will include then as well. It really says, well, we have to look at the complete kind of body of evidence to come to the judgment that a product is functionally safe according to the requirements. Of course, we have to look at the product itself. We have to test it properly, all the safety mechanisms, safety measures, diagnostics that are implemented. We also have to look at the complete, let's say, technical file. All the work products documents that have been created must be looked at. And we also need to care about systematic integrity. We also need to look at the processes, audit the processes, all that. Everything you have to look at. And all this compilation of kind of evidence of material, all that should combine meaningfully to an argument. And if it does that, then hopefully you can call it a safety case. That's the term that 26262 uses. It's not one, certainly not one that 26262 has invented. It has been around for many decades, since the 70s, clearly, I would think. But it's about building a safety case. That should give you this confidence, really. What is a safety case? Well, again, it's defined in the standard as the combination or the accumulation, meaningful accumulation of all the work products that you do. That's what the standard does. And actually for safety case, it's a discipline, safety case engineering, and there are universities, especially University of York, which has been pioneering this work, and they came up with even a notation for it, goal structure notation, a real fine thing, which you can use to really get structure and order and in this whole huge amount of documents that you will have to create. What I'll show here now is not really an introduction to GSN, goal structure notation, but it's a bit more a dummy or a toy version of it, but just to show the important aspects of it. Okay. First of all, you have a claim that ultimately the safety goals or the safety requirements that you have identified from the hazard analysis are appropriate, are correct and complete. That you have defined safety correctly, that you have done a good job in hazard analysis. And then if these requirements are implemented, refined, ultimately designed, implemented, refined completely and correctly, then we have safety, then we have achieved safety. Of course, we need to have some argument in place in order to support this claim of completeness and correctness as we move down to the lowest level. These arguments come from the evidence that we get when doing all the verification types of activities, doing the verification types of work products. That's, of course, testing, review, inspection, also the many analysis, safety analysis is in fact too a kind of a safety-focused verification activity. Even on the quantitative side, the calculations that we can then do based on a hardware component level, safety analysis using FMEA technique. Right. We're not quite done yet there's this word compliance. We still need compliance. Why would we need compliance with the standard tick off all the requirements if we have already correctness and completeness in the implementation? Well, it's because the evidence that we have here is not sufficient. We cannot test 100%, as already mentioned. So we have to rely on processes, you have to do process audits, review safety plans, and all these things. That gives us the arguments for compliance. Because ultimately, there is no absolute 100% proof possible. The only thing we get is a level of hopefully sufficient confidence. So something that is compliant with a SIL or an ASIL, it's no absolute term that this is absolutely safety. It's a level of confidence. Okay, and certification, what is certification in this context? Well, ideally, it's really about that. It's really about achieving confidence. The term certification is not really well defined, especially not in the standards. It doesn't appear anywhere in the standards. Okay. So certification can be anything. You can have certificates, for all kinds of things. What, of course, TÜV SÜD and all our competitors are with us who is in this area, TIC area, testing, inspection, certification. What we would want it to be is clearly certifications, approval, a listing, a recognition or something by an independent, accredited, competent, or notified, recognized, there are different terms for this organization or body. Okay, that's what we want to do. Certification often required by laws and regulations, okay? Especially in Europe, we know clearly the regulations or directives, and many of those for many years had in fact a direct link to functional safety via the so-called harmonized standards. Okay? You know very well in machinery what these are, and lift directive, there are similar standards, ultimately all referencing to 61508 standard. A bit of special case in medical devices, the standards can be considered to be a bit weaker there, but pressure equipment, ATEX, 61508 is at the basis of it. Automotive, not sure how many people work in automotive business in Denmark, probably not so many, was a little bit, could keep kind of too strong regulation out, especially functional safety was not really in, let's say, the automotive framework directive until now. Things are slowly changing. There is this awareness that autonomous driving, automated driving becomes more and more a public safety issue too. So we have now this regulation under this number from, you can see, very recent for autonomous driving system, ADS, up to a level 4. So really no driver responsibility, right? Within a defined environment, within a defined domain still, not everywhere, but as long as the vehicle is in that domain on, let's say, well-defined motorways or whatever, or in parking lots, or whatever it could be, that would be L4. And really interesting is that this is the first automotive regulation that we have that explicitly mentions functional safety, and in this case 26262, of course. So that's quite remarkable, at least we think as TÜV SÜD, we think that. And TÜV SÜD is clearly also accredited under all these regulations. We are a notified body under these regulations or directives, and the technical service in automotive covering that. Also at, let's say, more European or international level, I should say, the UNECE regulations. Lane keeping 2 is the first UNECE regulation in automotive which actually references a functional safety standard, 26262. Another geography is North America. I think automotive, they're not that far yet, but when it comes to workplace safety, installation safety, there are two. We have actually a quite direct link to functional safety standards. So the minimum benefit of a certificate is clearly, to show compliance with regulations and laws. That's minimum benefits. And we do have customers from time to time that really just want that paper. Give us that paper. We have this machine that has been safe for 20 years. Can you test that it's safe? That's what we get sometimes at a request. Okay. What we think from TÜV SÜD, really, and what I think also many of our customers think, and customers with good safety culture, is that certification should give an increased level of confidence, okay, that something is safe. Okay. That's what we want to offer as a service, and that's also what we need for our own sake. Okay. We need to make sure that the only asset that TÜV SÜD have, that's this blue octagon, that it is inspiring confidence in the safety. And what is certified? I think I've shortly mentioned all this at the start already, all these products primarily at all levels, typically as generic components, CIUC or compliant items. Things like ECUs, PLCs, sensors, drives, valves, say at a subsystem level, and then even at a component level, part level, complex ICs, and also software components, libraries, all that. Tools, already said, kind of a secondary job for us, because there seems to be a market drive to have tools also pre-qualified. There's definitely no regulatory driver for this, but the market requires it, and we get quite many projects for tools. Or process, just an organization, as maybe a preparatory activity before then really embarking on complex system development and compliance. And this is just training and passing an exam. Yeah. Well, if you want to achieve confidence, if a certificate should inspire confidence, then, well, how can it do that? This maybe triggers some sub-questions. Does the certifier really go in depth, checking correctness and completeness, understanding the technical design? Or is it maybe more a compliance case? You really cannot know what certifier does. Do they just tick off boxes and requirements? Or do they spend the time and effort to really, in a project accompanying manner, work with the customer, go inside, understand the complex design inside out? Okay. If you do that as a certifier, if you claim to do that as a certifier, as I would definitely claim TÜV SÜD does, then the big question is, to what extent do you do this? You cannot definitely redo the complete verification part of a project. That would be a ridiculously expensive certification project. So you have to get smart about it. Okay, and this means you have to spot checking, you have to do sampling, but not in a random way. You have to do it in an informed way. Okay, the challenge is to get confidence, of course, within a limited amount of budget. Clearly. And all this is only possible if there is sufficient technical competency in the certification. You must understand the technology, you must understand the application. And also, is it a one-off certification or is it a surveilled one? Is there a yearly follow-up? All right. What does TÜV SÜD more in detail? Well, to achieve that confidence, we work clearly development accompanying from the start, ideally. We cooperate with the customer, give immediate feedback to all the steps, all the products, all the work products or documents that have to be done in accordance with the process of the standard, covering all applicable phases and work products or documents. Roughly, we distinguish three types of tasks that we do. The most important one, and maybe 80% of the effort really is review, document-based, work product-based review. Typically can be done off-site. Some key work products, especially architectural ones, requirement-related ones, also analysis documents. Work products, by the way, which also 26262 wants to have confirmation reviewed, so we have kind of an overlap with what 26262 requires there. So there we really have 100% review. We go very much in depth. We need to understand the architecture. We need to understand the requirements. That's like building a house, building a building. The statics must be okay. You have to look at that. When it then comes to the more detailed documents, implementation level work products and documents like source code or unit test, or also we can have huge F meters, right? A controller with 1,000 components, each has on average 5 failure modes. That gives a huge F meter table. So we will not look at every failure mode and see whether they calculate it properly. But we know from our understanding of the architecture where the weak points are, where it is interesting to dig a bit deeper, drill a bit deeper. And also we have 2 then typically on-site activities. One is a test witnessing. So we have to, also our accreditors ask us to do that. We have to do on-site test witnessing. Select some test cases, go to the customer, and observe them as they are executed or re-executed by the customer. Not to find faults, but really to get confidence in the ways of working of our customers. Okay? If we should find a fault in this testing, if a test fails here, then it does actually mean that we have not done a poor job in review. This is something we should have already seen, ideally, at review. Yeah. So this is not about fault finding, this is about establishing the confidence in the ways of working by our customers, which we want to give a certificate. And last one, obviously, is the auditing aspect of it. Okay? We have a proper audit with an organization, going through the process, specific requirements of the standard, a dialogue with customers. Ultimately, we want to see that there is good safety culture present. We communicate typically by review protocols and checklists. We have a whole infrastructure of it. Review protocols are really used to exchange information. And we take all the discussions, all the meetings that we need to maybe discuss technical details until all the findings that we have are actually resolved. Yes, all these checklists and review protocols, so we need a whole infrastructure for this, a process for this as the basis for our accreditation. That's just to impress you a little. We won't discuss this, but that's all the dark blue boxes that shows where we intervene, let's say, as certifier in the project with the customer, where we have a review protocol or a checklist or a test report or whatever. How to initiate a functional safety certification with TÜV SÜD, should you be interested. Very informal, just an email to me or someone else at TÜV SÜD. We can give you a template for a request for quotation, which has a lot of important questions for us to understand really what effort is for us to be expected to be able to build the confidence. We need to have, of course, good understanding of the product, technology involved, what is the functional scope, functional complexity here. Also very important, to what extent pre-certified components are used, right? I think, of course, it is a big difference whether someone uses just a standard processor and develops all the software themselves, or whether they use pre-certified components, pre-certified, pre-qualified processors, pre-certified, pre-qualified low-level software components like HAL or STLs and so on. And also whether it's the first time for you or whether you have some experience in functional safety, That's important too. You get a quote back, and then of course you order, and then we get started. That's it. You submit work products as you do them, following the process, and you will get immediate feedback from us by review protocols. Okay? So we continuously work with you, accompany you throughout the complete development project. And we can have all the meetings, even workshops, as necessary to really come to solutions if we have findings that are hard to resolve. And then it may end up with certificates like this, if it's from TÜV SÜD. Just to different levels we have here: subsystem level, safety PLC, IC level, microprocessor or soft IP, as in this case, or also pure software-only components, software-only elements, SUC elements, like this example here. So these are certificates that are published by the owners. We only publish certificates where the customer wants that. Okay, that's clear. Yeah, and the last 2 slides with some good advice. Many of that is quite obvious, and much of that I think I already mentioned. Ensure basic understanding of functional safety within your organization. That's important. Training, really, we do recommend it if you're really new to it. That's the basic. Or maybe hire someone who's able to do that, or work with external partners. Involve TÜV SÜD or the certification partner as early as possible. That's really important. Basic quality management should exist. Something in direction of ISO 9000 with the main supporting processes like change management, release management, also skill management or competency management, all these things that are required by the standard. Ideally, you have that already as let's say, a quality conscious company, okay? And do not have to reinvent it. Okay? And even further than that, good practice in embedded systems and software engineering should be there too. Okay? Good quality, good level of testing, documentation. If you have that, that is 80-90% of the standard, especially on the software side, maybe 95% of the standard. Okay? Functional safety standards do not require something out of that would not be common sense, that would be rocket science or anything exotic. One thing I want to repeat over and over again: requirements traceability, very important, and ideally supported by tools, really, because doing this manually may work for a simple system, for a simple, I don't know, STO on a drive may be okay, but as soon as it gets more complex, you want to have tool support for requirements traceability. We had many projects PLC projects where they're trying to do everything manual. It is the horror, okay? It's really something we strongly recommend. And then pre-qualified components, I already said this, pre-qualified tools, also don't have to bother about qualifying your tools or compilers and all that. Yeah, so that's of course another recommendation. When we say pre-qualified here and you want to have an accredited certificate by TÜV SÜD, then also this pre-qualification means that it must be done by another accredited body, another TÜV or who else offers accredited certification. Only then we can accept it black box. Only then we can accept it on face value. If that certification is not accredited, then of course it still helps if there is good documentation available from the vendor, from the chip vendor, or whatever the component is. But we have to formally evaluate it ourselves then. Okay? And that's of course a cost factor. That's why we ask for this. That's an important question in our RFQ template. Do you use pre-certified components? And who is the certifier? Are they accredited? That's important. Common pitfalls. One is poorly defined, understood interfaces. And that's, of course, very often the case if it's not really maybe a generic component, but a bespoke solution for a customer. See this in marine. We have marine customers very often where they kind of find out, okay, we need this. Our customers get approached by their customers, tell them we need this SIL thing. So, okay, and then they go ahead and make a system, marine control system, navigation system based on redundant safety PLCs and all kind of stuff, and have great architecture come to us, and then we find out, well, what is the input? What are the sensors? What are the joysticks or whatever that the captain uses? Or we don't know. Are you clear that that must be still compliant too? And are your interfaces prepared for this? Well, we haven't discussed so closely with the customer. They're not very competent because they have to go back to their customers, and then the project stops for 3 months because their customer finds out that they have to, of course, have the same safety integrity level on their side too. Yeah, that's one thing. Another thing is also for generic components. Drives, for example, every drive today must have at least a safe torque-off function. So you can almost not be in the market if you don't have safe torque-off. So we do have customers who then quickly do something, but they're not clear about which components they should hook up to. What kinds of PLCs do you want to get connected to? What is the, let's say, the electrical concept of the input? Is it a dual pole, or is it a 2++ or plus-minus switching, or is there a serial data phase or serial data communication? You must be very clear about these things, otherwise you maybe do a product that is not as successful as it could be if you reflected all possible interfaces, all possible other industrial safety components you want to get connected with. Power supply, then secondary voltage regulation. That's very often an Achilles heel. You remember that redundant block diagram before? Yeah, great, but if they are supplied by the same power supply, if there's an overvoltage, your redundancy is gone. Okay. If you have a claim of category 3, category 4 at least, or HFT1, then this will apply also to your power supply. Okay? You have to have redundant secondary voltage regulators, or at least a redundant monitoring of your voltage supply to be able to claim fault tolerance or categories 3 and 4. Smart sensor diagnostics, if you have complex sensors. It's a bit the same thing as up here, right? Complex sensors, you cannot cover them by simply comparing anymore. They must have their own internal diagnostics. Add functional safety as an add-on, very difficult because you cannot just add some safety-rated software. You have to establish freedom from interference. And normally you can only do that really if you also spend some additional hardware components, especially because you need, especially for temporal separation, you need an additional clock at least. Okay? You need 2 sources of time information, otherwise you cannot achieve independence, freedom from interference from a timing perspective. Spatial separation, I think you can do a lot software level-wise, but when it comes to timing, you may have to change your hardware architecture, right, to fundamentally change your product in order to be able to add functional safety or make your existing product functional safety compliant. Duplication, even still by simple duplication of a product, same issue, that's common cause issue, you need diversity. Also a difference between the 2 main standards, they work a little bit differently. Need to be aware of that. Proven use, well, a whole big topic. Short answer is, that is TÜV SÜD answers, not allowed. You don't, we simply send you back home if you want to apply proven in use for software. Yeah, F-meter, classical fault, that faults which actually are dangerous detected are classified as safe faults. That's very often very hard job to say, okay, if this, because you know from your design, well, if this goes wrong, well, it will be caught by this and it will go into a safe state, so you mark it as safe. So that's, we always see these faults. Even experienced customers, it's so hard to abstract from the fact that you do have safety mechanisms, diagnostics already. So we always have comments, always try to find this one here. So yeah, be aware of this. Also, if you do products for both standards, lower level products, make sure that no effect faults are considered differently in these two standards. So 26262 in fact allows no effect faults to be classified as safe faults. So they help you to get a good metrics, SPFM and LFM. Not so in 61508, no effect faults must be kept out of the SFF, safe failure fraction calculation. So that's, there can be some incompatibilities between the two standards. Unit tests by and claiming structural coverage, I should say, by just generating test cases from source code. Okay, that's not sufficient. Structural coverage must be achieved by requirements-based testing. Of course, you can apply test case generation, you can apply the Tata tool, it's a great tool, but ultimately you must be able to trace the test cases back to requirements. Okay, that's, you want traceability. That's very important. Yeah, further good information under these links. This is an excerpt, I think, from these top misunderstandings about functional safety. There's a webinar around it, webinar about tools, tool qualification, how to select a tool, and about selecting components, in this particular case, motor drives. There's a webinar about the product-specific functional safety standard for safety-related motor drives. Yeah, this is who we are. We are 70 functional safety engineers, most of them in Munich. 50, I think, 20, they are scattered around Europe and the rest of the world. Few in Europe. I'm located in Denmark. For example, we have some in Asia and also some in North America. Yes, that's my contact. So further questions, inquiries, and so on, always welcome to contact me. That was the last slide. Thanks for your attention.